Thank you very much, Father Gannon, and thank you all for inviting me to come and speak to you today. As you said, my name's James. I'm a climate science researcher at Oxford University. And what I'm going to do today is talk to you about some of the background of climate science, so how climate change has been taking place over the last, say, 150 years, what the science tells us about what might happen in future, and some ideas about how we can act to prevent the most sort of damaging impacts of this change. So yeah, climate change in the past, climate change in the future. You will have come across the Paris climate targets, which were signed in 2015. These set targets for keeping the global temperature to below a certain level of warming. I'm going to talk about that and how we can stay below them. What are the ways in which humans are putting all this carbon into the atmosphere, and then how can we tackle our emissions? So I have a few little graphics to show you which hopefully work. If you look at this series of concentric circles here, what you're going to see is an animation of the average global surface temperature going from 1850 to 2017. The baseline, 0, is in the middle, and the two red lines on the outside represent warming of 1.5 degrees above this pre-industrial average and 2 degrees above this pre-industrial average. So those are the red lines that the Paris Climate Agreement states that the world is committing not to crossing. Hopefully this will now work. Okay, so each line we can see the world average temperature in each season. And since the kind of mid-20th century, that temperature has been increasing rather fast. And at 2017, in some months of the year, we're already approaching the 1.5 degrees target. Okay, I don't know how well you can see this. It's the 1780s, and the only country emitting carbon dioxide into the atmosphere at any appreciable rate is the United Kingdom. Into the 1820s, 1830s, it's still just the United Kingdom. Bit of Holland and Belgium now. America's starting to take off, but it's mostly the UK. Germany, so for over 100 years, the only country emitting was Britain. Japan now taking off. Industry spreading across Europe. You can see mainly in the UK and Germany, and across the eastern seaboard of the United States. China now becomes significant. We're into the 1970s, globalization is occurring, industry is starting to shift to Southeast Asia. South Africa takes off. China and South Korea now dominant. And that's the picture of emissions we can see today. So this burden is shared across the world, but we can see that the United Kingdom is the country that's been emitting the most for longest, which I think bears some thinking about. So, I apologise for the number of graphs in my presentation. I'm trying not to make it too much like a lecture, but please bear with me. What we have here is climate change in the future. So, as scientists, we use climate models to make projections of how the world might change in the future. A climate model is essentially what you use to make a weather forecast that you'll see on the TV every evening, just run much further into the future and at a kind of global scale rather than a regional scale. It's less precise than the weather forecasting model, just for cost reasons, but it's the same underlying idea. On this graph, the black line represents historical temperature. So here we've taken climate models in the past and we've run them with kind of observed amounts of carbon in the atmosphere to see if they can reproduce the past temperature, and they can. The multicolored lines represent 4 possible futures. The red line at the top is the hottest one, and under this scenario, we could reach, on average, up to 6 degrees above average warming by the year 2100. This obviously is a scenario we wish to avoid. 6 degrees of warming would be pretty catastrophic. You're looking at complete melting of ice caps, huge sea level rises, that kind of thing. Not necessarily by 2100, but certainly within the century after that. Unfortunately, that's also the scenario that we are most closely following at the moment. The other scenarios which are lower indicate that it is possible to keep the climate to below 2 degrees of warming by 2100 if we take the right sort of action. Worryingly, there is also the potential for warming to be much faster even than the high red line. That's because of feedbacks in the climate system which are not well understood. For example, some scientists think that if the world continues to get hotter, the amount of low cloud in the tropics might decrease. Cloud acts to reflect sunlight back into space essentially and keep the world a bit cooler. So if the amount of cloud decreases, then we're suddenly receiving a lot more radiation from the sun, and that could heat up the world a lot quicker, a lot faster. So there's a lot of uncertainty in how fast the world could actually warm if we get to the higher end of emissions. We just have to try and not get there so this doesn't become a possibility. And that is just the kind of thing that we can experiment with in our computers. So yeah, in 2015, the countries that were signatory to the UN Framework Convention on Climate Change's Paris Agreement signed off on this. They committed to holding the increase in the global average temperature to well below 2 degrees Celsius above pre-industrial levels, and to pursue efforts to limit the temperature increase to 1.5 degrees Celsius above pre-industrial levels, recognizing that this would significantly reduce the risks and impacts of climate change. Now, this was received as a historical document, really, the first time that an actual temperature target that we could avoid was signed and pursued by nations. Of course, one significant nation has now decided that it doesn't want to follow this, but hopefully they will see sense in the future. So how do we stay below this target? I think this is my last graph. This represents now carbon emissions. So the black line on the left shows the line that we have been following, and that little red dot is where we are now. If you follow on to the right, those are possible directions that the future could take, and then the column on the right shows what kind of level of warming you would expect. And you can see if you follow the black line, the slight sort of upwards trend that it's going, we're looking at warming of 3 to 4, maybe 4 to 5 degrees Celsius at our current rate of emissions by 2100. Now, recall that the Paris target means that we need to keep it below 2 degrees, and ideally to below 1.5 degrees of warming. And if you look at the right-hand side, that is definitely still possible if we follow the green, the blue, or the purple line. You'll also note that the amount of carbon dioxide being emitted as a whole in the world in these scenarios reaches 0 at about 2050, and indeed proceeds to become negative in the lowest scenarios. So that doesn't mean just stopping emitting carbon dioxide into the atmosphere. That means actively taking out of the atmosphere more carbon than we're putting in. So this is called the net zero target, followed by net negative emissions thereafter. Net zero is seen as key because one of the difficult things to understand about carbon emissions is it doesn't really matter how fast you're emitting them. What matters is the total amount that gets emitted. So because carbon dioxide, once it's in the atmosphere, hangs around for about 100 years, even if you reduce your emissions, the carbon that you are emitting now is still going to hang around in the atmosphere for about 100 years. So we're still locked into experiencing global warming. The planet will continue to get warmer regardless of whether we drop emissions to 0 now, because we're locked into a certain amount from what we've already emitted. So the challenge, therefore, is to keep that warming at a safe level by reducing our emissions essentially to 0, so we don't lock in any additional warming in the future. Now, this is a significant challenge, but I think it is an achievable one. It wasn't my last graph, sorry. I'm used to talking to undergraduates, but you'll pick up this stuff much faster than they will. Yeah, so here is essentially a graph of which sectors of the economy contribute most to carbon emissions. This is global, and from 1960 to 2014. We can see the biggest contributor is electricity and heat production. The world is becoming more interconnected, technology is advancing at a rapid rate, and this means that there's a greater demand for electricity. Also, as countries in the global south develop, their demand for electricity, heat generation increases. And the cheapest way to get electricity and heat is by burning fossil fuels. You know, they are essentially an ideal source of energy. You dig them up out of the ground for very cheap, you set fire to them, and you can generate however much electricity or heat that you want. It's just to have the rather unfortunate side effect of slowly suffocating the planet. But, you know, It's nobody's fault. They didn't know that was going to happen when it was invented. Transport is also a major contributor. Manufacturing industries and construction. So that's not just the creation of buildings, although that's very important. Cement production is a major contributor to climate change. That's also buildings themselves. So buildings are a major contributor, particularly in the UK, to climate change. Heating them, maintaining their electricity supply and so on. Efficiency savings to buildings are a major way we can combat climate change. Residential buildings as well. And then the other sectors thing at the top is essentially agriculture. Time is ticking. So this is a website that we built at Oxford University. We worked out that the amount of carbon that can in total be in the atmosphere in order to stay below 2 degrees is actually a very conveniently round number. It's 1 trillion tons. You can see there, when I took this screenshot, that the amount of carbon in the atmosphere was 635 billion tons. What this shows essentially is live data. I'm going to see if I can get it up for you to show you how this works and what it can teach us. But essentially what we have here, we expect the trillionth ton will be emitted at a nicely precise date, the 27th of January 2035 at just after 9:10 in the evening. So set your clocks now. But it would not be released if we reduced our emissions every year by about 3%. Now, I think that's an achievable goal. What this figure is teaching us is that although it is a significant challenge to keep our emissions below this safe level, it is something we can do with gradual cuts to emissions year on year for the next few decades or so. So what are our options? For a start, we need to reduce our emissions. The challenge here is that it's harder to do this in some sectors than others. For electricity generation, solar panels, wind power, particularly in Scotland on the train up, I noticed that there were wind farms on every hill between Penrith and Lockerbie, which was pretty impressive. There are lots of options here. Unfortunately, for some sectors, it is quite difficult to reduce carbon emissions. So we have electric cars, we have electric trains, we have electric buses. This is all doable. No one has really worked out how to make an electric aircraft or an electric container ship, and this is a real challenge. Carbon reductions in some sectors cannot be offset by increasing air travel. We need to reduce emissions from buildings. This means essentially legislation. New buildings need to be built to very high energy and insulation standards. Old buildings need to be retrofitted. But it remains the case that there will probably be some sectors of the economy we cannot completely stop emitting carbon from. We're still going to need to grow rice, for instance, which emits methane, which is probably the most powerful greenhouse gas. So some element of carbon capture and storage is likely to be needed. This is what I was talking about at the beginning, where we essentially take carbon out of the atmosphere and store it. This might sound like a kind of science fiction technology. A quite effective way of doing this has been invented a very long time ago. It's called a tree. Trees are good, let's have more trees. Unfortunately, you plant trees now, they might not reach their full potential for another sort of 30 years. So some kind of industrial way of doing this needs to be developed. The sort of chemistry behind this is known, but it's yet to be introduced on a large scale. That's something we really need to be looking into in the future. There is suggested a way of generating electricity that would actually not only reduce emissions, but lead to negative emissions. If you grow biofuels and burn them, and then you do carbon capture on what you've burnt, you're reducing the amount of carbon in the atmosphere. This has yet to be proven as a technology. Carbon offsetting, you've probably seen this in the news recently. It's the idea that if you fly, you can then pay someone to go and plant some trees for you, and then you can feel good about yourself. We're less convinced about this on a large scale. Just partially for that reason I just said about growing trees takes 30 years or so. Will these companies that offer carbon offsetting still be going in 30 years' time? How can we make sure no one will chop the tree down to grow biofuels? So although this can be used on a smaller scale, on a large scale it's not really a solution. It's just kind of taking the emissions and moving them somewhere else. We will, of course, need to adapt to a hotter world anyway. Climate adaptation will happen as a virtue of necessity. That needs to be driven both by the science, but also by our values. What do we want to protect? And what things do we consider, like, say, coastal assets? Should we retreat from coastal towns, or should we do as much as we can to protect them using seawalls? These are the kind of decisions that need to be made. And the biggest risks are the kind of runaway global warming. It just gets faster and faster as a result of feedbacks, and also the issue of climate justice and equity. So the idea that people in poorer countries have less ability to adapt and less responsibility to climate change, but also they will suffer most. So it's important that richer countries recognise their responsibilities on the global scale. And I leave you with a couple of quotes to think about. Well, there's a lot of quotes to think about today. Douglas Adams said, "I may not have gone where I intended to go, but I think I have ended up where I intended to be." In the context of climate change, what we need to do is get emissions to net zero by 2050. As scientists, we can suggest ways to do this, but we're not being prescriptive. We're not saying, you should do it like this, you should do it like this, or you should do it like this. The challenge for politicians, religious groups, companies, etc., is to work out ways of doing this that will keep us within the target. Antoine de Saint-Exupéry said, "As for the future, it is not a question of predicting it, but of making it possible." So, as a climate scientist, I can predict the future. It's a nice skill to have, but it's not everything. A weather forecast is only useful if you have the ability to put on a raincoat, right? So what we need to do, again, is recognise the challenges and then do our best to adapt to them and to mitigate against climate change. That's pretty much it from me. I think now you put your egg timers on.